Hey once again, and welcome to this video. In the last video, I've shown you the list of instructions that can be used to program the IAS machine. In this video, I'm going to show you examples of this said programs. Particularly, I'm going to show you how meters are converted into feet, how Fahrenheit is converted into Celsius, and how factorials, or rather the fourth factorial, is computed without loop, similar to the analytical engine. So in this case, we represent the IAS computer in a worksheet. How, However, we no longer represent this in terms of the Jacquard loop or the input device because according to the stored program concept, the instructions and variables will be contained similarly in memory. So here to convert feet into meters, we just have to multiply it to a constant value of 3.28. So our program is composed of about 10 words, with the first word being a jump to the first instruction. I'm following the convention that is used in the IBM PC where the first command is used to jump to the next valid instruction. Because as you see here, the words 1, 2, and 3 are not valid instructions. They are used to contain data. So jump 4 to 19 is jump to the word 10, which contains the first valid instruction of load M1. Secondly, we are using the jump address with the operand 0 to 19 to indicate that we are going to the jump to the left part of 4 of address 4 because address 4 has a right part which contains a second instruction. So here is how the program works. The first command jumps to the to 4L, which will load our uh, input value of 4. We can change this to any value you like. And then we will mul M3, or rather M2, which will multiply whatever input value is with a constant 3.28. And the memory variable 3, or rather, there, will be used to store the result. So let us start now. When we jump to 4L, the first command is load M1, which stores a value to the accumulator, the value of which is 4. And when we say mul M2, the accumulator, which is currently 4, will be multiplied to the value in address M2. That's 13.12. And then when we say store M3, we are storing the value of 13.12 to memory address 3, which is our final result. Now, jump 5R is jump 520 to 39, which means jump to itself. This is how a halt is usually represented, especially in a machine that does not indicate a halt. Now, let me take you to the Fahrenheit to Celsius conversion, similar to the analytical engine. In this case, we have a different set of variables, with M1 used to store our input value, and M2 is used to store the multiplier, or rather the subtrahend of 32, because the first thing to do is to subtract 32. The multiplier 5 is stored in M3 and the divisor 9 is stored in M4. M5 will be used to store our final output. So when you say load M1, the accumulator copies the value in M1. And we say sub M2, the accumulator now, whatever its value is multiplied by 32, which is the value of M2. No, subtract, I'm sorry, sub M2. It should be subtract. Okay. So the accumulator becomes 100. The next command in 7L is mul M3. This means that 500, which is the value in the accumulator, will be multiplied by the value of M3, which is 5. And the next command is a div to divide the value by 9, which divides the accumulator by the value of M4. And we store the result to M5. M5 here stores our final value. And we do a halt at 8R. So it has the same logic as that of the analytical engine, except that this time we are using the accumulator. We don't have an output register, a separate output register. Now let me proceed to the fourth factorial, which we use to demonstrate the analytical engine. In this case, I have written a program which is a translation of the analytical engine version. Likewise, the first command is a jump to a valid instruction. The memory addresses 1, 2, 3, and 4 are not valid instructions because they're used to contain data. In which case, M1 is our next multiplier or first multiplier. 1 is our M2 is our decrement constant of 1, and M3 will be our uh, partial our temporary variable, and M4 will be our partial product. Now let's start right away. When we say load M1, the accumulator is copied from M1. It makes it 4. And then we say store M4, memory 4 copies the value of the accumulator. The next step will be sub M2, which subtracts the accumulator by the constant decrement in M2, which is 1, which makes it 3. And then we say sub M2, and then store M, rather, sorry, it should be here, the 4 should be here. And then we say sub M2, so this will be this minus 1, it becomes 3. And we store M1. So M1 will be our next multiplier. We copy it from the accumulator. Remember that when we say store M1, memory address 1 will copy the value from the accumulator. The next command at 7L is mul M4, which means we will multiply the accumulator by the value at M4. So this is equals 3, which is the accumulator, times the value of M4, which is 4. Actually, in this case, we are computing the first partial product. And when we say store M4, we're copying the partial product, or the which will later also be the final result. And then we repeat the process by computing the next multiplier. We load M1 to the accumulator. So the accumulator becomes 3. And then we say sub M2. Okay. When we say sub M2, the accumulator is deducted by the value of 1, which is in M2. And then we store M1. We use M1 to store the next multiplier of 2. And then we load M4, which is our partial product. We multiply it with M1, the AC, we multiply with M1, which is 12 times, no, M1 is 4, equals, it is 2 rather, times M1, which is 24, and we copy the accumulator by store M4. By store M4, we copy the accumulator to the variable 4. And then we proceed to computing the last final product. So we load M1, so M1 equals 2. We compute the next multiplier, sub M2. So we have the accumulator 2 minus M2, which is always 1. Okay. And we load M4, which we store M1, which means that our next multiplier will be 1. And then we load M4, which is our previous final partial product. So the accumulator becomes, the accumulator becomes 24. We mul M1, M1 now is not 1, so equals 24 times 1, which is our final product. And then we store M4. So M4 is our final product, which is 24. And we go to a halt by doing a jump to 14L. So which illustrates the simple programming of the IAS. In the next video, I'm going to show you a sample program that is used to perform conditional branching, similar to the CF and the CB of the analytical engine. See you then, and bye for now.